The ways that we're going to see reactions occur are using curved arrows. These are used to show how electrons move as bonds are breaking and forming. In this first example here, we have a base you can think of as our nucleophile or our fishing rod, and it's going to go fishing for an electrophile or a hydrogen. We're going to start our arrow at the electrons, and that's going to go fishing for the hydrogen, just like you would fish with the pole. Once we hook that hydrogen, it becomes BH. The electrons go on to the A here, and that forms the extra electron pair here, giving it a minus. There's 4 main ways that electrons move in polar reactions. The first is a nucleophilic attack. If you are wanting to be a less violent person in this world today, you can refer to it as a nucleophilic hug. The second type of mechanism is the loss of a leaving group. The third is a proton transfer. And these are most common in acid-base reactions. And the fourth is a rearrangement. In the first type of mechanism, the nucleophilic attack or hug, pi bonds can also act as nucleophiles. In this first example here, we're going to see a nucleophilic attack or hug. If you recall, nucleophiles are electron-rich species, so this is our nucleophile. The electron-poor species is the positive, this is the electrophile. Our nucleophile is going to come and give a hug to the electrophile, so these electrons go from here to the positive, so we're trying to hook that positive. So this was our carbon chain before. We formed a new bond to that Cl. So that is a nucleophilic attack. In this example here, electron-rich species is the nucleophile, which is the negative. This electrophile is created from the partial positive, partial minus, so this is our electrophile. We're going to send our hook over here. That will leave. And then everything that was here comes along for the ride. So I have 1, 2, 3 carbons, 1, 2, 3. So that would be the product. So we also mentioned that pi bonds can be nucleophiles. In this situation, the pi bond is the nucleophile. This is a molecule that can induce itself to having a polar bond. So this is our electrophile. So the nucleophile can attack there. And after a few steps, we'll get both BRs across the double bond. So only 1 carbon. So only 1 carbon from the pi bond uses the 1 pair of electrons to attack the electrophile. I didn't show the whole mechanism here, so we'll see that more as that comes up. In the loss of a leaving group, we have a heterolytic bond cleavage, where an atom or group of atom takes the electron pair. In order to have a loss of a leaving group, you have to have a group that leaves, which in this case will be the Br. So I'm going to label that as leaving group, or Lg. The electrons will just break, and we'll discuss later on what makes a good leaving group and why the group leaves. So this bond is going to break. These electrons will go on to the Br. We have our Br here. It now has this extra electron pair, so it's Br minus. When those electrons left this carbon, it left it deficient, so that becomes positively charged. Sometimes you have to use more than 1 curved arrow to show the loss of a leaving group in this situation here. So these ones, that's missing an electron there. So these electrons, right, so this structure is missing a double bond right there. In this situation, we have an electron pair going in to form the double bond. These electrons will kick down to here. This goes in to form this double bond, and that will get kicked off there. So we redraw. So if I follow my arrows, I created a new double bond here. There's one here. There's one here, and the Cl becomes Cl minus. So I don't expect you to memorize how to do those arrows right this minute. This is just showing you how these arrows can occur. In a proton transfer, this is usually 2 arrows, and this is a fishing scenario. The fisher person has an electron lone pair. It's going fishing for the hydrogens, and it hooks one in there. When it grabs that, these electrons go back onto the oxygen. When oxygen is short a pair of electrons, so it took one of its lone pairs and is now bonding to the hydrogen, this becomes positively charged. And then we get water from this molecule here. So that curved arrow, the first one is fishing for hydrogens, the second one sends the electrons onto the oxygen. The deprotonation of a compound is sometimes just shown with an H plus or minus above the reaction arrow. So when we do proton transfer, sometimes you can abbreviate it as plus minus H or minus H plus, something like that. So in some cases for a proton transfer, they may not show arrows going from the water, but this will just do that. Call it H plus minus H. And there's a lone pair, and then we have plus H. A lot of times you need multiple arrows to show the complete flow of when a proton is exchanged. So that oxygen's going to grab this hydrogen. That's going to put an electron pair there. And we can show resonance structures of this. So this step is the proton transfer. So that can be abbreviated plus minus H or PT for proton transfer. In rearrangements, carbocations can be stabilized by neighboring groups. Increasing the substitution increases stability of a carbocation. A methyl carbocation, this is primary because there's one carbon group. 2 carbon groups make it secondary. 3 carbon groups make it tertiary. So carbon generally does not like to be positively charged, but if it has friends around in the form of other carbons, those carbons can help support that positive charge by pushing their electron energy into that positive charge to stabilize it. When carbon has less friends, like in a primary, it does not stabilize it as well. So with more groups here, this is increasing stability. So there's 2 types of carbocation rearrangements. One is a 1,2 hydride shift, and in that case, the shift will occur from the next door carbon and only occurs if you can make a more stable carbocation. So in this case, if a hydrogen moves to this carbon right here next door, that hydrogen moves here, that means the positive charge will switch places with it, and now this was a secondary carbocation, and it becomes tertiary, which is more stable. And sometimes if you don't have a hydrogen available, but you can shift a methyl group, that can pop over here. The methyl group goes there, and the positive charge switches places with that, which again makes it more stable. All right, in this practice problem slide, we're going to try to identify what's more likely to be nucleophilic or electrophilic. In the first example, we have amines, or a nitrogen, which is electronegative, but we have an actual positive charge on it. So if there is actually a positive charge on it, this is going to be an electrophile. Cn has a minus, this is nucleophilic. Br plus is electrophilic. In this case here, we don't have a charge, but we know nitrogen has a lone pair. This is partially negative, partially positive. That one's going to be nucleophilic. So the first mechanism that we're going to look at is the addition of HCl to ethylene. We have ethylene, which is going to act as our nucleophile because we said pi bonds can act as a nucleophile. Hydrogen chloride, or HCl, is going to be our electrophile. So we have our C from the ethylene. And then we're going to add an H and a Cl across the double bond. This falls into the FGT category. This is also an electrophilic addition. So this electron-rich ethylene is a nucleophile that is going to add HCl, which is electron poor, to the molecule to make HCl. If we look at the energy diagram here, this is that of ethylene, which is pretty low in energy. It takes quite a bit of energy to form that carbocation, or to go through the formation of forming that product. So this is the energy that it's going to take to form a carbocation intermediate, which we'll see on the next slide. Then there's another transition state where the Cl is going to attack the new electrophile that is formed, and then when you have the new product that is formed, that is going to be lower in energy, which is the driving force for doing this reaction. Alright, so looking at the mechanism, we have the first thing that's going to happen is we're going to have a proton transfer. So an alkene plus HBr is going to be a proton transfer. We're going to go fishing for that hydrogen, and those will come down there. So when I go fishing, one of these carbons gets the hydrogen. The other one, this pair of electrons went to form a new bond with the hydrogen. I took electrons out of this carbon as well, so this is now positively charged. And this is the carbocation that forms. So carbocation is a positively charged carbon. This is the intermediate. So in that process, Br- was also kicked off. Okay, so after we do a proton transfer, we want to look for our nucleophile and electrophile. Br is negatively charged. This is my nucleophile. This carbocation here is positive charged. This is my electrophile. So we're going to get a nucleophilic hug here. So the bromine's going to come and give the electrophile, or that carbon positive, a hug. This H was here, and then we add Br. So there's two different types of arrows going on. We have the proton transfer. That creates the carbocation. The bromine then which is the nucleophile, gives the electrophile a hug, and that will form a new bond from the bromine to the carbon. So this is a two-step reaction. When we look at these transition states, we start with the reactant. It has to overcome an activation energy to go through the tough parts, like forming the carbocation, and then once it forms the product, it's much lower in energy. So this is the transition state. The activation energy, or EACT, is the energy that it needs to overcome that first hump. So another type of reaction that we'll see is addition of hydrogen, which is also going to be categorized as a reduction reaction. In this case, it's using a catalyst to increase the rate of the reaction by giving it a different way to get there. So this reaction here is an alkene with H2 and a palladium catalyst, which adds hydrogens across the double bond to form the alkane. So the catalyst provides a mechanism with a lower activation energy. If we look at an energy diagram here, you have reaction that has this big hump here. This is uncatalyzed, but when you add a catalyst to the reaction, it removes some of the obstacles by giving the reaction a different route to get there, or just lowers activation energy. Okay, so if we're going to show the mechanism for this is the HCl reaction that we just saw. So we're going to start with a proton transfer. So I'm just going to draw an arrow here. The first one is my plus minus H, or proton transfer. So I have my pi bond is going to go fishing for a hydrogen. The electrons that are between there are going to go onto the chlorine. And we'll talk more about that in the next chapter. The carbon that has more hydrogens here, that has two H's, is going to get another hydrogen. So that hydrogen wants to be surrounded by its friends, and so that's why it goes there. And we'll also talk about that in the next chapter. But when we do that, the carbocation goes to this carbon right here, which is going to be a tertiary carbocation, which is the more stable one, which is another reason why the hydrogen goes to that carbon. So I have that carbocation forming plus the Cl minus. In the next one, I'm going to do a nucleophilic hug, where the Cl minus is going to act as my nucleophile, and this is my electrophile. So nucleophile is going to hug the electrophile, and that will form this product here, which is the same as drawing it that way. Okay, so you can take a stab at doing these practice problems. So I'm going to start with this first one here, HCl across a double bond. The product, I'm going to add an H and a Cl. The reaction that is occurring is an FGT addition. And the arrows that are used in this one are a proton transfer and nucleophilic hug. Okay, and if I follow the arrows here, I'm going to form a new bond to this carbon, and then that comes along. The reaction, this is an addition. Arrows here are nucleophilic hug, and also loss of leaving group. Okay, so here's just a look at different naturally occurring alkenes. This is a big class of compounds called terpenes, and you may have come across some of these in your time outdoors. Some of the more familiar ones maybe for you are beta-pinene, alpha-pinene, camphene. These are smells from pine trees, and that different camphor smell if you are familiar with that one. Other terpenes that you might see are beta-caryophyllene, which is the smell of cloves or pepper. There's many floral smelling ones. We have bisbolol, which is in pink over here. This lavender scent, terpepinene, which is a woody lemon lime smell. We have limonene, which we'll be extracting from orange zest in a few labs from now. Myrcene is an earthy and musky scent. Geraniol is one of these that's used in perfumes. It has that rose smell. So we see these alkenes all the time in nature, or we smell them. A lot of them are used now for essential oils. People are using misters for that. And this next slide, you can see the different structures of the terpenes. And then I'll show you why in the next slide why they're called terpenes. But this is the structure of limonene. We have two alkenes here. Garofylline is a hoppy smell. There's two double bonds as well, and some extra things to the structure. The different eucalyptol has a bicyclic ring. We have linalool. This musky myrcene smell has a different structure. And then you can see those there and see each of those descriptions, how people use these for essential oil or aromatherapy. So the reason that they're called terpenes is they come from this structure here, which is 2-methyl-1,3-butadiene. That's called an isoprene. They can attack a molecule of itself. This is a naturally occurring molecule to form myrcene. So this one unit can attack different units of itself in different ways to form the structures. If you look at all of these, although it's hard to see right now, all of these came from those terpenes attacking each other in these structures here as well. You might get an alcohol coming in there every once in a while, but all of those structures came from this isoprene structure. Steroid hormones come from lanosterol. That's a different terpene. This is a triterpene. And all of these come from that same isoprene unit as well.